Hello everyone and welcome to yet another Zozin session. How about that? So today I want you to take a look at some interesting esoteric programming language. It's a concatenative programming language, right? So, and one of the probably widespread class of concatenative programming languages is a stack-based programming language. One of such languages is Porth. Porth is the language that we've been developing for quite some time. You can find this language on GitHub, I'm pretty sure. So let me actually give you the link. gitlab.com/Porth. Right, I hope I spelled it correctly. So here it is. You can find it in here, Porth. And there we go. So, and what's interesting about concatenative programming languages is that any operation in that language operates on the stack, right? So, stack is a data structure where you can push the elements on top of the stack and pop the elements from the top of the stack, but you cannot access the elements at the bottom of the stack, right? So, it sort of emulates the actual stack of things, like stack of plates. For instance, when you have a stack of plates, you can only access the top plate, right? But you can't really access the bottom one unless you want to break everything. Right, so if you never heard about such a data structure, just Google up stack data structure and you'll find a lot of interesting information to learn from. Right, so and in Porth, for instance, any operation operates on so-called data stack, right? So a number, just a number in that language means that you push that number on top of the stack, right? So, and this, for example, pushes the number 5 on top of the stack. Then if you put another number, that pushes another number on top of the stack. And if you do plus, it's an operation that pops two elements from the top of the stack, sums them up, and pushes the result back on top of the stack, right? And then you can do print, and what print does, it just pops the elements from the top of the stack, prints it, and that's it. I think it doesn't do anything else yet. So basically it removes the elements from the stack. So for instance, this thing will print 11, right? So because it will put 5 on top of the stack, then 6, then we'll sum them up, and then we'll print the result, which is 11. Right, so this is a stack-based programming language. So the language that I want to take a look at today actually uses a different structure. Excuse me. It uses Deque, right? And it's literally called a Deque programming language. So let me actually put it in here. Deque, right? And here's the idea. Deque is an ad hoc example by Christopher Dickens. I don't know who that is, but maybe it's a famous person in concatenative programming language community. For concatenative language that is not a stack language, it uses Deque instead. To quote from his message to concatenative mailing list, allow me to present the Deque language that I just made up. 1 exclamation mark pushes a 1 to the right of the Deque. So I presume, like, basically the placement of the exclamation mark denotes to which side of the Deque you're pushing, right? For those who don't know, the Deque is a data structure where you can access both of the ends. As I already said, in the stack, you can only access one end, right? In a Deque, you can access both of the ends. You can push to the right and push to the left, pop from the left and pop from the right, right? So in here, on top of like having an operation, like pushing a number or maybe summing up numbers, you also denote the direction on which end you want to do that, right? So if the exclamation mark on the right, you push to the right end, and if it's on the left, apparently you push to the left. The same with the operation. And I presume a basic program in that programming language looks like this, right? So it's almost like a concatenative programming language, stack-based programming language, but you also denote the side of the Deque you're working with. So what's interesting is that this creates basically two stacks, right? So essentially you have two separate stacks that are sort of connected to each other. So if you underflow one of the stack, you start consuming the other stack, but this is already technical details. So, and yeah, effectively you have two stacks. And my question was, is this language even Turing complete, right? So is this like a proper programming language that you can use to develop like algorithms and stuff like that? And to explore that, today I wanted to implement a rule 110 in the Deque programming language, right? So rule 110 is a one-dimensional cellular automaton, right? Which I usually use to demonstrate that a particular language or a particular system is Turing complete. Not only I do that, people do that quite often. For instance, I think the Turing completeness of the HTML5 plus CSS3 system was demonstrated to be Turing complete by implementing rule 110. I think, I don't know for sure, but I think that's what people did. Right, and I want to do the same with Deque. I want to see if it is even possible to implement rule 110 in such language. And rule 110 is a very simple cellular automaton, right? So you have a one-dimensional state, as you can see. It's a sequence of cells. The cell can be dead or alive, right? And you have a table that maps a sequence of 3 cells to a new cell, and you iterate through the cells with the window of 3, and you match these 3 elements with the table, and the table tells you like what's going to be the next cell for the next generation, right? And that way you generate the next generation, right? So when you repeat that process on to generate the next generation, and so on and so forth, and that thing evolves into something that looks like this, right? So this is a lot of generations. So maybe I can actually zoom in. Right, so it evolves into something like this, right? And it's been proven that this cellular automaton is Turing complete. So if your language can implement that, so your language is probably Turing complete as well. Right, unfortunately, like I don't think there is implementation of such language. This is basically just an idea, right? So we'll have to implement that language ourselves. Right, so we're going to be implementing the language, rather the idea, right? So I don't know if the syntax of that language is standardized even. I'm going to just like, you know, implement. I'm going to have a creative freedom on the syntax and semantic, but the main central point of semantic is going to be the Deque. And then once I implement that language, I'm going to implement rule 110. I think I'm going to actually do the following thing. I'm not going to do this at 2 separate steps. I'm going to be implementing rule 110 and the language simultaneously, right? So essentially my idea is going to be like I will implement a little bit functionality to advance the implementation, right? So then I will see what other features do I need in the language to continue implementation. Then I implement this feature and then I'm going to use them. So that's going to be the plan, right? So that's going to be the plan. All right, so let's go ahead and create a folder, Deque. Okay. So I think I'm going to use Python so people can understand what I'm doing. So DequePy, right? DequePy. Let me put a shebang in here, user bin environment. We're going to be using Python 3. Of course, you should use Python 3 in 2022. Imagine using Python 2 in 2022. Anyway, so let's create an entry point. Right, so this is going to be an entry point. And in the entry point, we're going to say something like hello world. Right. So maybe I also want to make this thing executable, and let me try to run that. So here is hello world. So let's create a file rule 110, right? And I think I'm going to use just a Deque extension. So let's try to implement this program, right? So let's actually implement enough interpreter to interpret this specific program, just to test things out, right? So first thing we need to do, we need to read the whole file, I suppose. So if I remember correctly, you just open the file, right? So rule 110 Deque. I think you can also say it, that you open it for reading like in C. So with as f, right? So can I do stuff like that? Okay, so it actually opened the file. And I think I can simply read the entire thing. There we go, I actually read the entire thing. That's pretty cool. I wonder if I can split everything by a space, and there you go, so I've got something. That's pretty cool, so yeah. So the next thing we can do is essentially interpret that program. So we can save it as a program, so here is the program. Right, and then I'm going to have some sort of IP, which usually stands for instruction pointer. It doesn't stand for internet protocol, right? I'm going to say that I'm executing starting from the first instruction, right? And while IP is less than the size of the program, while it is a valid instruction pointer, I'm going to try to right, I'm going to try to implement, I'm going to try to interpret a particular instruction. So I suppose we have two situations in here, when the instruction starts with exclamation mark and when the instruction ends with exclamation mark. So if, let's put it this way. So I think I'm going to say word program IP, right? If word starts with exclamation mark, right, we're going to do one thing. If word ends with this thing. Otherwise, I think for otherwise, I'm gonna put some sort of error, right? So I'm gonna say false. Can I just do something like rise error? I wonder, I don't remember how to throw errors in Python. Can I rise error? Hello. Right, error is not defined. Runtime error. Yeah, okay, so let's actually use runtime error. Runtime error. I don't know. Direction of the command is not specified. So it would be also kind of nice to tell where exactly that happened. So I think I'm going to provide the number of the instruction, right? Of the instruction IP is not specified, and I'm gonna say F, right? So there we go. I'm gonna run this, and interestingly, I also need to increment this thing. Right? There we go. So in here, when it starts with this thing, we probably want to remove this thing. So this is going to be like that. Left word, and then if it ends with that, we want to remove it from the end. Right word. Okay, so that makes sense. Right. Right 3, left 5, and there you go. So that's pretty cool. Okay. So let's introduce the Deque, right? So as far as I know, Python has a Deque data structure, right? It does have a Deque data structure. So it's in collections. From collections, import Deque. From collections, import Deque, and I suppose you can do something like Deque. So here's the Deque, and if we put something like this, so this is the data, and then I can push into the data, right? So this is going to be 69. What are the other things? So let me take a look at what methods do we have in here. So we do have append, right? We do have append, yeah, we have append left, but we don't have a right, so we just have append. Append adds to the right, but to add to the left, you have to do append left. Okay, that's cool. Sure. Data append 35. Right, and then if I do data append left 36, okay, so it added there, and then I'm gonna do 69 just append. Okay, so that seems to be working. So now we have our data stack, right? So this is our data stack. So here we read the entire program, and here is the state of the execution. So I suppose here we'll have to take a look at what is the word, right? So if word is equal to add, we're gonna do one thing, right? So I might as well do something like rise not implemented. Do we even have not implemented? Yeah, but I'm not sure. Does not implemented accept any parameters? So I can do not implemented. Exception must derive from not implemented. It's kind of weird. So let me see, Python 3 not implemented exception. So I just want to throw an error. Not implemented error. Okay, not implemented error, but can I provide some message? Yeah, I can. Okay, cool. Not implemented error, and in here I can say instruction IP. Right. Not implemented, but maybe instruction add at here. Okay. Else if, what are the other instructions we have? So we also have sub, word, sub, sub, and here we essentially assume that word is going to be an integer, so I'm going to convert it to an integer, and since we're on the left, right, so this is the left, I have to do data append left, like so. There we go. So what's interesting is that here we should have a similar thing, right? So here we have a similar thing, but the only difference is that we append to the right. Right, which makes me kind of think, maybe we should actually put it like inside out, if you know what I mean. Right, maybe we can have something like a direction, or maybe left. So by default, let's put it as none, right? So by default it's going to be none. And in here, we're going to just move this entire thing outside of this condition. And this condition is going to be simply responsible for determining the direction, right? So it just determines the direction and also cleans up the prefix and suffix from the word. So here is, if it starts, that means it's a left, so it's going to become true. And here, left is going to be false. There we go. So we sort of separated these two things. So here's the word, then where the left is none, we determine the left, clean up the word, and then we check the word. All right, and then here, when we append, we only have to append to the left when it is left. Otherwise, we should append it to the right. There we go. So we basically compressed a little bit this entire thing. We don't duplicate this code anymore. Okay, so let me try the following thing. So instruction subbed at 3. All right. So the question is, how are we going to be treating the sub operation, because subtract is actually sensitive to the order, right? So 5 minus 3 is not equal to 3 minus 5. Well, I mean, the absolute values of these things are equal, right? But anyway, so essentially, in a stack-based programming language, right, so I usually subtract the top with the previous, right? So if I pushed 5 on top of the stack, then 3, then 4, right, and then I say subtract, I usually subtract top from the previous, right? So in that case, it will compress into -2. So, but here we're dealing with the stack, right? Here we're dealing with the stack. So I suppose when the operation is left, I'm going to be subtracting this element from this one, right? So it will basically end up like this. But when I do to the right, I'm going to be subtracting this one from this one, which will result with -1. So basically, I want to continue the idea of treating both of the ends of the deck as two stacks, right? So that means on the right is going to be stacked but mirrored, right? So that's going to be basically the idea, hopefully. And that means when I add something, when I subtract something, I have to first pop an element from this thing. Let me actually import the deck. Let me import the deck and take a look at its help. All right, so when I do pop, you can do pop left. It would be kind of cool if pop had some sort of an argument that tells you that you do left or right. But I'm not sure if it is easy to do that. So I think what I'm going to do, maybe I'm gonna have something like push data, right? And here we're gonna have left. So basically I want to hide this condition that I'll have to put everywhere every time I work with the data, right? So essentially if left, then data, so this is going to be a value, append left value, otherwise data append value. Okay, and then pop, right, left. If left, return data pop left, else return data pop. All right, so that way I don't have to do this kind of stuff. So left is the first one. So push data left int word, right? So interesting. Basically, I put that information into this function, and the decision, like to which end to put that, will be made inside of that function. So I don't have to think about it anymore. So now, if I want to implement sub, what do? I do a pop data left, and then pop data left. So essentially, if left is going to be false, it's gonna pop from the right, but this particular function doesn't even care about that. So, and then I'm gonna do b minus a, right? So this is b minus a, and push data left like so. As you can see, basically I've essentially abstracted away. I abstracted away the direction, so I don't have to think about it anymore. And in here we can do a similar thing: pop data left. Right, and then we push the data left a plus b. So we basically implemented everything, I'm pretty sure, right? So the entire thing is already successfully implemented. So let me see. Line 40 forgot a comma, right? So there you go. What else do we have in here? Pop data is not defined, even though I defined it, so I just didn't call it pop data. There we go. We can't see anything, right? Because this program doesn't really print anything. One of the things we can try to do, we can try to basically print the state of the Deque on each iteration, right? So just to see what is going on. So print data, right? Okay. So let's take a look and see if it actually corresponds to what we want. So we have to put 3 to the right, makes sense. Put 5 to the left, 5, 3. Put 2 to the left, 2, 5, 3. Then subtract, and that subtracted 2 from 5. Actually, no. It's subtracted from the right, so it means subtracted 3 from 5, ended up with 2, and then add. And there you go. So that makes sense. I don't see any problems with that. That's pretty cool. So, alrighty. We've got a simple implementation from the example that was sent in the email, I suppose. Maybe there was some more stuff, but the email itself appears to be very short. Right, so there's only one example in here and just a little bit of a text that I didn't read. So anyway, let's try to implement rule 110, like actually implement rule 110. So my idea is the following. We're gonna keep the first generation like this, right, in the Deque. So we push the entire generation. Then we're going to have some sort of a marker at the end of that generation. So, and computing the next generation is basically taking the triples of these things and figuring out the next value, right? Figuring out the next value and so on and so forth until you reach this marker, right? You reach this marker, that means you computed the next generation. Then you move that marker to here and repeat that process. So you see, Deque actually kind of helps you to do that, right? So you are consuming from one end, but pushing to another one until you reach the end, and there you go, you have the next state to consume. And you just basically like rolling the computation of the generation. So that should be actually pretty straightforward, I think. All right, so let me see. So we can try to initialize the state. So I'm gonna have bunch of things in here. I don't know how many I want to put in there. So let's say we're gonna have 6 of them, right? And I'm going to put all of them to the left, right? So all of them go to the left, right? And essentially I want to put like 1 in here, right? So 1 is going to be here. I suppose whether the cell is dead or alive is going to be determined by whether it's 0 or 1, right? So that means we can denote the end of the generation with any number that is not 0 or 1. Let's actually put 2. So we're going to say that 2 is an indicator that this is sort of the end of the state, right? So this is our special marker. Okay. So, and let me see. So if I try to run it, as you can see, we actually put everything in there, and I think that was a mistake, right? So, oh yeah, it put all of that to the left, but it put all of that in a separate, in a different order. Yeah, that makes sense. So what about we actually put all of that thing to the right? You know what I mean? Yeah. So something like this. Let's actually put it like this. Okay. So it makes it super easy to reverse this entire stuff. I really like that. Okay. So what's going to be the next thing? We need to maintain the window of 3, right? So essentially, the usual way to roll the window of 3 cells and matching it against the table is to take these 3 elements and compress them into a mask, right? So essentially, these 3 elements should become a single number, a single mask, right? So, and since it's a binary number, right, 0 or 1, you have 2 to the power of 3 different states in here, right? 2 to the power of 3 different states, and basically 8 of them, right? So you basically have 8 of them. And every time you want to proceed to the next element, you essentially shift this thing by 1 bit and add another bit, right? So that's usually how it goes. That's usually how it goes. All right. So we also will need to implement loops, right? So I think loops is going to be also very interesting to implement. But before we go and implement the loops, let me make a small break. I want to actually make a cup of tea. And after that, we're going to try to implement the loops. All right. I don't want to spend too much time on implementing loops. Like fancy loops, I would say. So I'm going to implement a very simple system of labels and conditional and unconditional jumps. So let's put it this way. Any name that ends with a colon is going to be basically a label, right? So then, if you refer to the name without the colon, you basically push an address of that specific instruction onto the stack, or rather a deque. So that means you can provide the direction in which direction you want to actually push it, right? So whether you want to push it to the right or whether you want to push it to the left, right? So, and then I'm going to introduce 2 instructions, which are GMP, which always jumps to the address on top of the deque, rather on top of the current stack, depending on the direction, right? And GMP if, right? And GMP if basically jumps to the address only if the top of the stack, is true, right? So that way I can organize conditional and unconditional loops. For instance, I can do something like this. So here's the loop, then I can do loop GMP, and there we go. So everything I put in here is going to be repeated indefinitely unless I check some sort of condition, right? Right, I check some sort of condition. Of course, like you always have to provide the direction. And then jump out of the loop. Jump out of the loop. There you go. So one thing I noticed about this language, the direction is actually kind of noisy. Right, the fact that you always have to provide the direction, like where do you push the value, left or right, actually kind of noisy, so I really don't like that. And also, is it not equal, or is it equal for the left end of the deck? It's I suppose the author didn't really think through the syntax and the implications of the syntax of such language. But yeah, there you go. So I suppose you can even put something like this, right? So this is basically the loop. Might as well even put it like that. So this is the beginning of the while loop, right? And this is the end of the while loop. Something like that. Might as well maybe do something like this, and yeah, it's not that bad. So let's actually implement like a very simple program to test this thing out. So let's actually put loop Deque, and here we're gonna simply put 10 in here, and we're going to organize a loop. We're going to organize a loop that always repeats. And here, how we're gonna check this entire thing. I suppose I want to duplicate whatever we have in here. Then I want to push 0 and then check that this thing is greater than 0. Right, this thing is greater than 0. Right, so I'm checking that this thing is greater than 0. It would be more convenient to put the condition first and the label to the out later, like so. Yeah. Okay, so I think it's going to be a little bit easier like so. So, and in here, then we have to do 1, and we have to subtract that 1. Okay, cool. So let me do the following thing. So right now the file name is sort of hard-coded, right? So I suppose we want to unhard-code it. Right, so from, I don't remember where it is located. It is located in OS, or is it located in system? Right, import sys args or argv. It is located in argv. Okay, so import sys. Now we have sys. Okay, so let me print argv. Just want to see what's going on. So it contains only Deque, but if I provide something like loop Deque, it also contains this thing. So if length less than 2, we have to print some sort of error, right? So we're going to print error, no file path is provided, right? Then I'm going to exit with 1. There we go. So, and then we can do the following thing: file path equal argv1. File path, cool. So, print program, exit 1. Okay. Argv, it has to be sys. Okay, there we go. All right, so I already see a problem. So our tokenization, so to speak, actually split by spaces, but it doesn't split by lines. Right. Okay, I wonder if you can do something like split lines, right? Okay, but maybe you have to convert it to a list. Well, I mean, no, it's a function. Okay, so we split by lines, but then we also want to actually split each individual line by spaces and sort of concatenate everything together. So let's actually use list comprehension for that. Right, for line in split lines, for word in line split by spaces, we're gonna be spitting out the word. There we go. So that thing works. So that thing works really well. And if I put rule 110, so this is a rule 110, we can actually, just load different files. So the next step I would like to do in here is to collect all of the labels. Right, so since you can actually jump to the labels that you haven't read yet, we need to sort of iterate through the entire program once and pre-collect the addresses of all of the labels. Right, I think that's quite important. Okay, so let's actually create labels, and this is going to be a dictionary. And what we're doing here is essentially, I think we have to iterate it as a range. So this is going to be a range, length of the program for IP in range. Right. Word program IP. So if word ends with this, what we have to do, we have to add the address to that word in here. Right, and then we can do the following thing. There we go. So here are the addresses of all of the labels. So in loop, right, in loop we have only 2 labels. And here they are, right, loop and end. But since we're going to be referring to these labels without the colon, I think when we put them in here, we have to get rid of the colon. Yeah, there we go. So without that thing, it would include the colon, which is not what we want, actually. Right, as you can see, it includes that colon in here. We have to get rid of it. Yeah, there we go. That's a bit better. That's a bit better. Okay, cool. So we load the program, we ignore the lines. Interestingly, maybe we can even do something interesting with the lines. All right, for instance, ignore the ones that are commented out. We can even introduce a simple comment system. I think it's a good idea. Let's actually try to do that. So here's the program, right? I'm gonna put it in here. So here's the program, and if I put something like this in here, right, it will not comment this thing out whatsoever, right? It will not do that. So what we have to do, we have to put a condition in here. So here is the word, and then here's the for, and here's another for. So if line starts with this thing, actually does not start with that. Right, but you can have spaces in front of this entire thing, so we have to trim it. Right, so can I just do something like trim left? And I wonder if that will work. So there is no such thing as trim left. Okay, so if I do this thing, it's kind of difficult to see what the hell is going on. Okay. So there's a strip at least. Okay, let's take a look at help. Strip. So return a copy of the string with the leading and trailing white spaces. But what if I want to actually do that stuff only on the leading, right? Well, I can do on both of the ends, but for some reason I just want to do it on the left just in case. So there's a L strip. I can see L strip. Returns a copy of the string with the leading. So I suppose leading is on the left and trailing is on the right. Yeah. So essentially I can do something like this: space, hello, space, L strip, right, and that remove this entire thing. Okay, that's actually pretty cool. So if I go in here, so this is gonna be L strip, right? It doesn't start with that. And there we go. And it didn't work. Very cool. I wonder why. What the hell? Excuse me. If not start. Really? What? Okay, let me get rid of this thing. So this is gonna be just a line, and let me... Ooh, no, I'm an idiot. I see. It's not a line, it's... I see. This one's a little bit more complicated, right? This one's a little bit more complicated. So I think we can limit the support for the comments only for the start of the line, right? So yeah, essentially, if you want to comment a particular line, you can only put that at the start of the line. So this is the limitation of the comment system. I still want to have some sort of a comment system to just disable some parts of the code, because I think it is pretty convenient. Right. But I don't want to spend too much time on the comments. It's just like, I think it's a waste of time at this point. Okay. So there you go. There you go. Let me try to execute this entire stuff and see if it does anything. Direction of the instruction 1 is not specified. Okay, so let me see the direction of the instruction. Oh yeah, we don't handle the labels, right? So as you can see, we check for whether it starts with exclamation mark or ends with that, but we never check if it's a label. Label never starts or ends with this thing. So if word ends with this thing, I suppose we just skip it, right? So I'm pretty sure we just skip it in this specific case. But I can't really do a continue, right? I can't do a continue because I need to do IP plus 1 before I can do all of that, so it's not particularly great. It's not particularly great. Interestingly enough, I think we'll have to have a discrete change of IP, because sometimes, for example, GMP will not do IP plus 1. It simply will not do IP plus 1. It will set IP to something. Right. So I suppose because of that, we probably need to put IP in here, right? And then here we can just do continue, I suppose. Right. And furthermore, I suppose printing data makes sense at the beginning of the loop, because why not, right? And also once after the loop, right? Once after the loop. There we go. That should be it. And let's try to execute, and that is very interesting. So it keeps pushing some stuff, which probably indicates that this thing works, which is rather interesting. I'm not quite sure why it keeps looping. Oh, okay. So yeah, so it keeps pushing this thing and it doesn't advance anything. So essentially what we need to do, we need to check that if something is IP or not. Okay. I see. Essentially, I'm not quite sure why it keeps doing all of that, because I would expect this thing to push this thing, then encounter that stuff. Oh yeah, okay, so we'll still have to do IP plus 1 in here. Yeah, okay. Yeah, so and I would expect it to fail because it cannot convert dupe to integer, right? So that's what I expected to do in here. All right, so elif word equal dupe, and let's go ahead and implement that. So what we're doing here, we just pop data from a specific site and push that thing back twice, right? So we're duplicating it. Okay, so the next one is greater, right? So this one is greater. So we're going to do pop data left, and then pop data left. And what we're pushing back, this one is rather interesting. All right, so because if I put 2, 3, then I do less, I would expect it between that and that. So if I pop that first, so that means this one becomes A, this one becomes B. So I need to do B less than A, push data left, right. So what do we have in here? So we have false, and then you try to pop from an empty queue. Which is rather interesting. Okay, so there is probably bug within the program in here. All right. Okay, cool. So we compared in here, and we never encountered anything like end. Right. I expect in this specific case, to see end, but it didn't work for some reason. I probably know why, because I again forgot to increment this in height. All right, and then I see end, and end is not a correct thing. Okay, so now we're starting to sort of like refer to labels that we have collected, right? To labels that we have collected. So now we probably need to wrap this integer call to into try catch, right? So, and we have to do something like try this thing, and then if we catch accept, I think it's accept value error, right? Value error, and then in this case we just use word to look up in a dictionary, like labels. We need to find labels and just go there, and we just push that data in here. And by the way, if I try to find something in a dictionary that it doesn't have, it returns, like, it throws an error. Okay, so that's fine. And then we're gonna increment it by 1. Okay, cool. Let me see. So then we have an invalid literal jump if, right? So I need to implement jump if. Word equal jump if. So what about jump if? Jump if expects a label on the top, right? So here is the label, pop data left, and then we have a condition, pop data left. If condition is true, right, this one has to be addressed. It's not a label, it's specifically addressed. We do IP equal that specific address, otherwise we do IP +1. And that's exactly the reason why I put IP +1 in all of the branches and not at the end, because for one specific case I should not do IP +1, I must set it to something, right? So this is annoying part of software development, that sometimes you have like a lot of conditions that can be generalized except one, and just because of that except one, you have to do a lot of useless work. Well, you didn't really have to, but I mean, it becomes error prone anyway. Direction of instruction 7 is not specified. Actually, I should probably also print the name. Right, I don't see any reason to not. Direction of instruction word at position. This is not specified. Okay. Instruction space. Right, there is nothing in here. It is empty. It is straight up empty. I'm quite surprised. Let me take a look. So if I try to print the program, do I have any of the empty instructions anywhere? Oh yeah, I do. Would you look at that? I do straight up have empty instructions. That is fascinating. So maybe one of the things I have to do, if word greater than 0. Right, so that way I never include them. So that's nice, and then we compute the labels a little bit later. Okay, so what else do we have in here? Internal... Oh, okay, so I forgot that we have a sub instead of that thing. Interestingly, so when I do a subtract, right, so I do 3, 1, all right, then sub, what I'm subtracting in here is A from B. Am I subtracting A from B? I think I am subtracting A from B, so that should be fine. Right, so now I can just do that. All right, so, and then we have a GMP, and GMP is actually unconditional jump. It doesn't need any condition, right? So that's why it's called unconditional. Elif word GMP, and here we extract the address left, and then we simply jump to that address. That's literally the entire operation. Okay, cool. It became -1 at some point. That is very cool. Okay, huh. That is so cool. I'm fascinated, because why did we end up with -1 in here? How did we end up with -1, and how did we end up with something like 11 in here? Oh, because we set greater. We need greater or equal. Yeah, greater or equal. But then we'll have to implement that as well, which is not that difficult to implement anyway. Right, so elif word greater or equal, pop data left b, push data left b greater or equal. Well, I mean, right. Pop from empty. What has happened? Excuse me. This one works. And this one should work as... Okay, that's beautiful. Okay. So as you can see here, we are repeating a thing. So maybe I should also introduce something that prints a number, if you know what I mean. Right, I mean, why shouldn't I do that? Right, something like dupe print. Right, so dupe print, and that should print the number. Okay. Just to test things out, so we can disable the tracing. Right. Word equal print, something like this, and then I can do print pop data left IP +1, and let's introduce some sort of a variable that indicates that we're doing tracing. Right, tracing is false, and we only print the data. So we also do continue here. We only print the data if the tracing is enabled. Print data, yeah. If tracing, only then do the data, and if tracing, there we go. Okay, so and here is the loop. Here is the loop, and for here we can do a true. Right, so we implemented like a very simple loop system, right? So it's just like allows you to place a label in there and just like jump there. So, and that means I don't have to implement while loops. I don't have to implement even if conditions, because I can implement if conditions via the conditional jump. Right, so it's a very simple low-level approach. Right, doesn't require too much effort to implement all of that. Right, it's pretty cool. Okay, let's go back to our rule 110 implementation, and what do we want to do in here? Right, so I'm gonna do rule 110 deck, and here it is. So here we initialize this entire thing, and what we need to start doing, we have to probably start compressing these elements into the mask. So at the tip of the state in here, I want to maintain the mask consisting of these three elements, of this window of the three elements. So I'm gonna actually merge together these two elements, right? And I'm gonna merge the third one. I'm gonna merge the third one inside of the loop. So obviously we're gonna have some sort of loop in here, right? And here I just like unconditionally jump back, and then here we have an end, right? So we're gonna do some stuff inside of the loop, right? But before we go into the loop, I'm going to put 1 onto the stack to the left, right? You know what? I want to actually exit, right? But exit will require providing the direction. So will require providing the direction. You know what's interesting is that what if we allow not providing the direction? What if we allow not providing the direction? Because sometimes, what if I want to just exit that doesn't operate in the stack? What if you have words that simply do not operate in the stack? They don't have a direction. How do you represent that? So direction is needed only when you push that thing, when you pass it to push data or to pop data. Right, what if we simply do not care in here, right? We don't care. And if there's a word that doesn't require direction, it will like never deal with this left equal to none. But if it requires, that none will be passed to push data or pop data, and I suppose you cannot use none as a condition, or can you? If none, print hello, otherwise print world. Right, can you use it as a condition? I'm not sure if you can. Maybe you have to put a semicolon in here. So there's something syntactically incorrect about this thing, so I probably have to do the following thing. Right. So that means you can do that. Unfortunately. Okay, so basically it automatically converts to false. So that means here we have to do something like if left is none, right? We have to throw an error of some sort, right? But we have to probably throw an error that also tells some sort of information about what's happened. Because if I just throw an error, just do assert, left is not none, right, it will not tell me where exactly that happened, like the place where that happened, which is kind of a shame, right? But maybe the only thing I have to do in here is just like take these two functions and move them inside of the loop, but I have a feeling that they won't be able to access that value. Or maybe they will. Who knows? Will they be able to access to like IP? It's actually very interesting. So I have this weird idea. I have this really weird idea where I allow them to exist in this specific context so they know the IP as well. Is that a good idea? I don't know. Maybe it is. So essentially, if left is not none, I can raise a runtime error, saying something like direction. Directory. Did I say directory somewhere there? Okay, so I already removed the code for that printed an error, so I forgot what it said. Direction is not provided for let's put it this way, for program IP at IP, and then that is basically it. Actually is none. And since we have an access to left, maybe we don't have to pass it. Right, so it becomes really tightly, you know, coupled, which is probably not bad, but Okay, embedded literal. So what if I put something like this in here? All right, so direction is not provided for this at 7. So it does work. Right, it does work, but it leaves a little bit of a weird feeling. A little bit of a weird feeling. Okay, so maybe that's fine because it's a throwaway code anyway, right? So it's a throwaway code anyway, so it's okay to write a little bit of a crap, right? It's okay to write a little bit of crap. But if we're gonna write crap, let's actually write the crap all the way. Right, so let's put those things like literally down there. And not pass the left. Let's don't pass it. Let's say that it's gonna grab the left from its scope. So that way we never have to actually pass the left in here, right? And then query replace push data left, push data. And that was a bad idea. So we have to do something like this, push left. Something like this. But that's fine, I think. I think that's fine. Okay, cool. Now, so it's exit, and in here, if I didn't provide, it will say direction is not provided for 1 at position 7. Okay. So we need to implement exit now. Let's implement exit. Word exit. And I suppose we can just do that. Just like literally exit. Cool. And yeah, you can actually put like anything in here, like it won't care. Right, it literally won't care, so that's kind of funny. And direction is not provided at jump. Okay. And keep repeating itself. So, all right, this one is actually rather interesting. All right, as you can see, it keeps repeating itself. It's kind of cool that it pushes the address and then just keep repeating itself. Maybe we should put some sort of a prevention mechanism, but maybe it doesn't matter because you can always control C, right? If you're sort of stuck, you can always control C, so that's totally fine. Anyway, so let's go back. What I want to do, I want to put 1 on top of the stack from the left, and essentially shift to the right. Right, I want to shift to the right. So I'm taking whatever I have on top of the stack and I'm shifting it by 1 to the right, leaving a little bit of a space for the element in here. Right, for the element in here. And the reason, by the way, I introduced exit, so I can put exit in here to skip all of the code in here that I'm gonna get back to later. Right, so that's basically the idea. Okay, so shift right does not exist yet, so let's go ahead and implement that. So elif word shift right, so pop data, then like this. And essentially what are we doing is we're using this as the index to where to shift. So shift right, so it becomes B, and then we push data back. Right, we push the data back, ++1. Like I really like, so I said that this is a crap idea to like have these functions in here, but it completely abstracts away all of these implementations from the fact that we're dealing with a Deque. Right, so none of those implementations even know that there is a Deque and there is 2 different ends, right? All of that is sort of like, all of that knowledge is stored in here, and this is just like implementation that assumes that this is a stack. This is actually pretty cool. Right, so maybe it was not that much of a crap anyway, right? So it's actually pretty cool. Okay, so what do we have in here? So here we put like 1 and stuff. I'm thinking maybe I also, if I'm tracing, right, if I'm tracing, maybe it makes sense to print the word that we're currently executing, if you know what I mean. Right, I think that's a good idea. So literally, right, so word, and maybe even IP, right, can we do that? Yeah, look at that beauty. Right, so now we know exactly what we're doing, right, so that's so cool. Might as well actually use this stuff, right, and then something like this, and then something like this. Yeah, boy, looks like shit. Nice. Thank you, Emacs. Very cool. Okay, shift right. So though, if we're gonna be doing shift right, that means we'll have to. Yikes. Yikes. Because it's not really a result of that thing. So let's actually put it the other way around. So we're sort of indicating that this is the initial state that we put into this command. So that way it makes a little bit more sense. Okay. Now, so I shift it, and then I wanna OR them together. Right, I wanna OR them together. So if I try to execute all of that, it says that OR is not available, shr, elif, word, OR, and in here we just like do the pop and b, push data a or b, right, and then ip +1. There we go. So this is what we got. Well, it's not really visible because there's literally nothing in there, right? So there's literally nothing. But if at the beginning we had something like 1, we should have had like 1. Shift right didn't, because it has to be shift left. Okay, it has to be shift left, not shift right. Okay, so then we'll need to implement that. Shouldn't register for it. So shift left. Okay, so now it is 2, right? And 2 in binary form, right, 2 in binary form is 1-0, which actually corresponds to what I wanted to do. Cool. So 1-1-0. If it was 1-1, we would have had 3. I'm pretty sure. Yeah, there you go. We have 3 in here. So, but both of them have to be 0. Okay, both of them are 0. Cool. So we pre-computed the the thing. I'm gonna just like jump unconditionally here. Oh, maybe, I mean, I can always comment it out, right? So I keep forgetting that I can always comment it out. Yep. So, and the next thing we want to do, all right, the next thing we want to do, we want to essentially repeat the same thing, right? We sort of want to advance and consume the next element, right? Advance and consume the next element. Maybe, it depends. We also need to check for this marker, right? So we also need to check for this marker when to stop the consuming of that thing. All right, so I think I want to make another break. All right, so I ran out of tea. So, and after the break, we continue implementing this thing. All right, let's continue. So I think at the beginning of the loop, one of the things we have to check, that we achieved, like we reached the end of the generation, right? So yeah, so since we have this state, the 3-element window at the beginning, right? So at this point, we're gonna have something like state, right? So that state, and then 2 as the marker of the end. So what we have to do something like over, all right, over, which will copy 2 in here. Then we'll have to put 2 in here and check if it's equal to 2, right? And if it is, what we have to do, we have to jump to the end. All right, so that's basically how we achieve that. So that's the end of the loop. If it is not, right, if it is not, we can try to do this thing, right? So we can add that element to our mask. But before we can add that element to our mask, I suppose we have to also clean it up. So, excuse me, right, if we have this mask, we shift it to the left, right, we shift it to the left. That means we also have to get rid of this bit, right? That means just shifting it to the left once is not going to work. What you also have to do is apply mask, which is 7. So 7, as far as I know, it is equal to 1, 1, 1, right? So that's the mask. The first one corresponds to 1, this one corresponds to 2, this one corresponds to 3. So to 4, right? So, and sum of these elements is actually 7, right? So this one is 6 plus 1, 7. Okay, so and 7 in binary is 1, 1, 1. We can even double check that, I suppose. Right, if I go in here and then say bin, show me the bin of 7, it is 1, 1, 1, as you can see. So yeah, that's precisely why I do that. So I shift the current state to the left and then I clean it up. So I remove the 4th bit, like so, and then I do OR, right? Which makes this sort of operation differ from here, but not that much, because you can always just add it here. It's going to be equivalent, right? It's kind of pointless to do it here, but at least it makes it, you know, the same, right? So you perform the same operation of sort of consuming the element into the current state. All right. So, and let me see if we need to implement anything. So we need to implement AND. Let's go ahead and do that. So we have OR somewhere here. I can do elif word AND A pop data, then B, and then what we're gonna push is A and B and increment this thing. Do we need to implement anything else? We need to implement over. Okay. So I think I'm gonna implement it near the dupe, right? elif word over, right? So A pop data and then B pop data, and essentially what did we have? 1, 2, right? So this became A, this became B, right? This became B. So, and we removed all of them, right? We removed all of them. And I suppose I have to push back data B, data A, and then back B. And then +1. I'm not sure if it's gonna work well, so let me confirm. Right, so I'm gonna put exit in here, and I'm going to just put 1 and 2. Right, so here we have 2 elements. 1, 2, and we have that as well. If I do over, right, if I do over, I end up with 1, 2, 1, which is precisely what I would expect, right? So because this was the state, this was an initial state, and we copied the element over that one, and now we have this state. Okay, so that actually works. Okay, so that's pretty cool. So it does in fact work, and now we need to have equal. I'm thinking, should it be equal? I'm gonna actually call it like eq, because this thing looks like it's not equal, right? So it's actually called eq. Right, and now, where I'm gonna put that? I can put it anywhere, and none of that matters. Word equal A pop data B push data a equal b, ip plus 1. Right, what do we have in here? Direction is not provided for jump if. Okay, let's provide that. Okay, that's pretty cool. So it did the stuff, it did the thing. So, but then it ended in one iteration. So 23, that's... Oh, 23, it's an address, right? It's just an address. I see. It would be kind of cool to actually distinguish different types of elements on the stack, right? We can see booleans, the results of the comparisons and stuff like that, but it would be also nice to see the addresses, you know what I mean? But that means we'll have to add some additional information to them, but I just don't want to spend too much time on that, because it's a throwaway code anyway, right? It's a throwaway code anyway. Okay, so that means here we have now an index, right? So essentially how rule 110 works, let me go to the description. We have this table, right? You may notice that different sort of combination of cells form binary numbers. So this is 0, 1, 2, 3, 4, 5, 6, 7, and there's exactly 7 of them. And they map to one of the bits in here. What's interesting is that you can take those bits, right? You can take those bits and just turn them into a binary number, right? You can quite easily do that. So let's actually query replace tab with nothing, right? And this is a binary number, and then you can use that index to find that bit within that number, right? And you know what's cool about this entire thing is that if you convert this binary number into decimal, in the decimal form it is equal to 110. And that's the reason why the cell automaton is called 110, right? We already discovered that on our streams quite some time ago, but I just want to point that out one more time. All right, so, and the current state, we're going to use that current state as an index, right? So I suppose we want to duplicate that index, right? So this is a duplicate. And then I want to push 110, right? I want to push 110, but then what I need to do, I think I want to swap them, right? I think I want to swap them, because what I have in here is essentially the index, then I put this thing in here, then I need to swap them, And the reason why I need to swap them is because then I need to move that index, shift that index, right? I'll have to shift that index, but maybe not. Okay, index, right? I need to push 1. So, and if I do shift left, that will effectively shift this index by 1, which is not what I want. So that means I want to swap that thing first, right? Swap that thing first, and effectively only then it will shift this entire thing like so. And this is what we're gonna have at the end in here, right? So I suppose, which would then can, or with the 110. But before we can do that, I suppose we also want to duplicate that index. Okay, let me just put an exit in here and just see what we have at the end. We don't even have a swap, so we'll probably have to implement it first. So where is the dupe? Where is the dupe? So if word and then swap, pop data. So, and then if I push them in this order, right? So effectively I'll swap them, right? So 1, 2, swap, exit. 1, 2, swap, exit. And what the hell is going on? Why Ah, I see. Why? Because for the swap I forgot to do this thing. Alright, so, and it in fact it swapped them. Okay, that's cool. That is very, very cool. Then in here, right, I'm gonna have duplicate, right? So I duplicated this thing, I swapped it, I put 1, then I swapped it, then I did shift left, and that's fine. Okay, not really sure if it's worked correctly because there's too many zeros in here, so it's kind of difficult to you know, understand, but I'm gonna just continue. So after that, I need to push 110, right? I'm just pushing 110 and swapping it again, and then I need to do an AND to get the value out of that. So effectively, it's gonna stay 0. All right. It's gonna stay 0. So, and I suppose the next thing I need to do from here, right, is to transfer that value to the other end, because that value, actually not really. It's rather complicated because you have to, if you have an index, right, so if you have an index, some sort of an index, you have to do something like this, 110 and, right, and then you have to bring this thing back. So you have to use that index twice. Right. So which sucks a little bit, right? So it's kind of complicated to implement it this way. It's kind of complicated to implement it this way. It would be kind of cool if I could not only push a value, but sort of mark a particular value with a label so I can track that value within the deck, right? If I said something like mark with the name, and that name would appear with the deck so I could see that, but I don't think it's gonna work well, especially when you swap things around. So it is rather complicated. So you basically have to do that yourself, right? A 1, then 1, right? Then we swap, then we shift. So I'm using the right side because it's easier for me to think about that. So shift left. It's more like this. Shift left, 110. Swap and over. Shift right. I think that should work. I'm pretty sure. Let me actually go one more time. Right, duplicate index 1, swap, shift left, 110, swap, and over, shift right. So that's what we want, I'm pretty sure. Okay, and the last thing we have to do, we have to take that element and move it to the other side of the stack, right? So, and interesting enough, how can we do that? Is there any name for such operation, right? So take from one end and move it to another, right? So we need to come up with a name for such operation. Let's actually say toggle. So essentially, depending on what direction you put in here, it either move from right to left, right, or from left to right, right? So since we're doing everything on the left side, it will take whatever element you have on the left and just move it. And since I say move, let's actually call it move because it's smaller to implement. Right. And you just move it in there. And I guess that's basically it, I think. I'm pretty sure. I'm pretty sure. Duplicate 1, swap. So here I just want to keep all of the separations in here. Okay, cool. So let's go ahead and implement all of this stuff. So it doesn't know about the move, and move is going to be rather interesting, right? Word move. Right, so you're popping an element, and now you have to push it to the other side, but the direction is controlled by the element left. So maybe we have to do something like left, not left, and then push data in here. Right. Just to preserve the original direction, maybe we have to do something like this. Right, so yeah. So that's the result of using global variables. Okay, so let me try to test this entire thing just to see if it works correctly. Right, so if I'm gonna do 1, 2, 3, right, so what I'm gonna end up with, I'm gonna end up with 3 to 1, that's fine, and then I'm gonna move into the other, well, of course I forgot to do +1 in here, right, so, and what it did, it essentially moved from left to right, but if I change the direction in here, it will move from here to here. Okay, so that makes sense. Okay, cool. So that is basically it. Let me see. And yep, so if I'm not mistaken, this was the original state, right? So this was sort of an original state. After a single iteration, what we ended up with something like this, and if you move it like that, there you go. Interestingly, we lost one element, right? We lost one element, and the reason why we lost one element is because this should be the second one, because we're taking this state and then we're replacing it in here. So I suppose to sort of fix that, if you know what I mean, before starting the loop, we have to put 0 at the end in here, right? We have to put 0 at the end in here, at the right end, and I think now it will, yeah, it will produce something. Okay. So now if we take a look at the original state, so here is the original state. The original state, and what we ended up with. Yeah, so that's basically what happened. Okay, so but this is a single iteration, right? So this is a single iteration, and what we want to implement is we want to implement a loop. So this single loop performs a generation, right? Then only a single generation, right? It computes the single generation. And so it, theoretically, it should keep doing all of that until it encounters the marker, right? The marker of this entire thing. Okay. Let me see. Okay. Interestingly, so what we have at the end in here is essentially the index that we probably want to drop, right? We probably want to drop that index. We don't really care about it. So, okay, key drop is not implemented, so there is no such thing as drop. Let's quickly implement that. Drop. Well, you have to provide the direction. Did we provide the direction? Yes, we did. Deque. Pop data. IP +1. Okay, so now let's go back to the original state in here. So this was the original state. And then after all of the iterations, we ended up with this. Right, so as you can see, we iterated through all of these elements, we crunched through all of them, and we moved the next generation to the other side. But we again lost some of the elements, right? So there was 6 of them here, and there's only like 5 of them here. And this is probably because we have to pad with 0 on the right side as well in here. Right, so as you can see, we put 0 just to pad things in here, and then I'm gonna add another 0 just to pad again. So we're sort of like padding this stuff. Okay, so if I try to compute it one more time, and there we go. So this is the next iteration, right? This is the next iteration, and I suppose I need to prepare this state for the next iteration. So I need to move this marker to here to say that, okay, let's compute the next generation. So let me quickly do move like so, and there you go. So this is the next generation. So this is the next generation. The first generation was somewhere here, I suppose. Let me see. So I'm pretty sure this was the first generation. So let's go to here, right? And the second generation is something like this. Right, not bad, not bad, not bad. So that means to compute the next generation, we have to execute this entire stuff one more time, right? We have to execute it one more time. All right, so maybe I'm gonna actually put a little bit of space in here so we can clearly see. All right. We can clearly see, and yeah. So here we have initialization of the state. So this is the initial state, the first generation, and then another generation, right? Something like this. There we go. So that advanced it a little bit, but you know what? The tracing produces too much noise, right? So the tracing produces too much noise. You know what I want to do? I want to disable the tracing completely. Right? I want to disable the tracing, and instead of like auto tracing, I want to introduce a command, right? Just trace, that prints the current state of the data, right? So we trace it here, then we're gonna trace it afterwards after this thing in here as well. Right, and after this here, this thing here as well, right? So, and as you can see, I don't provide any direction because it doesn't matter, right? It just dumps the current state of the stack, of the deck rather. And of course, this thing is not implemented, so let's quickly implement it. Because why not? Why not? Okay, so I'm gonna print the data, right? So. And of course, I forgot to do +1. All right, look at that. But for some reason, I can't see the third one. Excuse me, where is the third one? That is really weird. There's only 2 of them. You see? It's kind of weird. Why? Do we put exit anywhere? No, there's no exit anywhere. So there should be... Is that because I didn't have a new line in here? Is that the reason? Okay, so if I remove that thing... Oh, and if I remove that thing... And if I remove that thing... Okay, so whatever trace I put in here, it never worked. How come? I think I know. This is because we have duplicate labels. God damn, I see. So I don't... Okay, I see what's going on. So I don't properly check whether we have a label redefinition. Okay, so that's actually quite important. So can I check if something contains it? So if I have hello, right, and so hello in true, anything else, false. So this is how I can easily check all of that. Okay, that's cool. So it's quite important when we collect the labels, right? So might as well do something like this. If word in labels, rise runtime error, label word already defined. Yeah, so that's basically what we can put in here. And if I try to run that, as you can see, labels, not labels, a single label loop already defined. Right. Might as well just put this thing in here. Yeah. So that means I have to give a different name for those loops. You know, I think the time has come to actually create like an outer loop, right? So let's create an outer loop. Right. So I'm gonna remove this thing. So all of that is inner, and then we're gonna have an outer, right? So this is the outer. An outer doesn't really have an exit condition, so that's kind of a problem. Yeah. So we can do something like this, sure. But we can always just do Control-C, right? So, yeah, whatever. Let's go ahead and just see. So did it, I think, believe it or not, I think it worked. So the only thing we need in here is just more space in here, right? So we'll just put it like that. Does it look like a rule 110? I'm pretty sure it does. So I feel like it does look like rule 110, but not really. So it's a bit sus, I would say, right? It's a bit sus. But I would love to turn this into like maybe characters of some sort, I don't know. Because it's kind of difficult to see. It is kind of difficult to see. But I think we're going somewhere. We're definitely going somewhere. All right. So when I do trace, right, so instead of printing data, can I turn it into a list? Right, so can I turn it into a list? Okay, so this is a list. And then I want to map this list. Maybe I don't even have to convert it to a list. Okay, I can say I just want to map this thing. Right, I take this x, and essentially if x, well, we can always do something like character, a character x, right? So nchs is essentially the following thing. So the zeros one, space, this, and 2. Let's say this is also going to be space. All right. So let me see. Why does it? Okay. So it's an object, but I want to turn it into a list. So that's what we got. And then I can probably try to join this entire thing, right? So list object. Oh, you have to do something like this, I'm pretty sure. Join. Yeah, there we go. It does look like, but this double thingy, right? So double diagonal line kind of looks a bit weird to me. I'm not gonna lie. So because of that, since I only put one, I put star on one, I think the easiest thing to do in here would be if x, so x, if x equal 1, else I don't remember how you do that, right? So this otherwise put space. I think it should work. Yeah, it did work actually. That's quite surprising. Okay, now I'm gonna go in here and let me try to put more stuff. Let me try to put more stuff. Okay. Did it make it bigger? I think it does. It does look like a rule 110. Right, it does look like a rule 110. Except for the part where we have this thing, and I'm really not sure. Maybe this is because I'm tracing something in a really weird way, but I don't think so. I really don't think so. Maybe I should trace only at the beginning. Right, so here is the... Yeah, okay. So that probably makes way more sense. Right, so I just put this thing in here and only then I trace that thing. Right, only then I trace it. Still a bit weird, but yeah. I guess that's basically it. I want to compare it with the Porth rule 110. Does the Porth rule 110 also has this double diagonal? I don't remember actually. It's kind of, I don't know why it bothers me so much, but it bothers me anyway. Okay, so Porth, examples, rule 110, Porth. Oh yeah, it also has this double thingy. Okay, so I think I'm just like misremembering something. So yeah, okay. It's pretty cool. It would be kind of cool to also limit the amount of these kind of iterations, but I'm not quite sure how to do that yet. I'm not sure how to do that. But yeah. So maybe we can store the amount of iterations, the amount of outer iterations in here somewhere, right? So this is where we can store them. And let's put it this way. So I can put something like 10. Let's say there will be 10 iterations, right? And then that means I can quite easily do the following thing. I can duplicate, but the right one, right? So I'm duplicating the right side and putting 2 in there and just trying to check whether this specific thing is still greater than 2, right? So in here I can put outer end, right? So this is outer end and outer end jump if, there we go, something like this. You know what? So, and that also means that here we have to do things slightly differently. Okay, I want to do 1 sub, right? So I just subtract 1 from that counter, right? I subtract 1 from that counter, duplicate it and check if it is greater than 2. If it's less than 2, right? If it's less than 2, we straight up jump to outer end, right? Straight up jump to outer end. So that's fine. So that means here, what we have to do, we have to check that it's not equal to than 2, but rather it is greater or equivalent to. Right. So basically it indicates that it's, you know, that it's an end and also it's a counter, right? So that's pretty cool. It's simultaneously the marker of the end of the generation and the counter for the outer loop. So that's cool. Okay, so maybe I can actually split this entire stuff into this stuff. Yeah, there we go. Okay, that's pretty cool. Okay, I need to run that, but I'm a little bit scared to run that. But anyway, okay. So I ran porth. This is not what I wanted. Okay, so we don't have a keyword less. Let's go ahead and implement that. Elif word. And I'm gonna just like copy paste this stuff in here and run it like that. And it didn't work. Thank you so much. That's very cool. Yikes. Ugh. Okay, so if I put this thing in here, it does some weird shit. It completely screwed up. Fuck, I completely broke it. Ah, shit. Okay. Okay, so let me just see. All right, I can always sort of like debug that, right? Let's put exit in here. Oh yeah, I need to enable tracing. Yeah, so I need to enable tracing, otherwise I won't be able to debug that. So that's gonna be true. So we even have sort of like a built-in debugger, which is kind of cool. Holy shit, okay. So maybe I need to reduce the amount of those things, just in case, right? So let's actually put some stuff in here, right? So that way we're reducing the amount of things. Then we put 1 at the end, so here is 1. Then we subtract, it becomes 9. Then we duplicate 9, that makes sense. Then we push 2. Okay, then we check that it's less, and it becomes true. Okay, so I suppose it has to be the other way around if it's greater or equal. Right, if it's greater or equal, only then we jump there. All right, so, and then maybe it's just greater. Still -1 or something, that's kind of weird, but okay. So let's disable tracing and let's take a look at what has happened there. And it's just like, okay. So let's put exit in here. Tracing true. So at the end, we ended up with some sort of a 0. Which is a good question, what the fuck? I see what the fuck is going on. Okay, so this is a completely different side. So I do over. So then we put 2 in there. And then we check if it's okay. It's too early, I would say. It is too early, so that means, yeah, my brain is already doesn't work, so I have to like step debug things like this. Okay, so but it doesn't really matter because I think we achieved the final goal. Yeah, there we go. So that's pretty cool. So I'm gonna enable more of these things. There we go. And oh shit, okay. Why doesn't it not continue? So I suppose at some point this thing sort of like becomes indefinite. Okay, so let's still enable the tracing. And let's fix that. So what the hell is going on? What the hell is going on? Maybe I need to make another break. Yeah, that's probably the case. That's probably the case. Okay, so we can clearly see that this... Okay, there was 9. So then 8. So I suppose I need to reduce this entire thing to 3. Just to reach the point when it becomes something. So there's 52. I don't know. Okay, so let me make a small break because I need to reset my brain, and after the break we'll take a look. All right, let's try to understand what the hell is going on, because it's kind of weird, I'm not gonna lie. Let me reduce the amount of things on this stack. Right, so I'm gonna exit around here. Right, so that's about right. Cool. Now I'm gonna select step debug. Right, so this is 1. And then the next step is gonna be subtracting that 1 from 3. Right. So we are subtracting that 1 from 3, so it should be 2. And it is in fact 2. Then I'm duplicating the 2, so now we're gonna have 2, 2. Right. And then I'm basically comparing with 2, so to do that I need to essentially put another 2 in there, right? So, and then after this specific comparison, it becomes false. I have a feeling that we have to do equals. I'm pretty sure. I have a feeling that we have to do equals. It's actually EQ. Right, which will guarantee quitting as soon as we reach 2, right? Because if we go below, it may screw up the logic in here. So it's kind of dangerous. Let me actually put a 4 in here just to see that it's false, right? But as soon as it hits 2, it should be quit, right? Essentially, it should be quitted. And in here we put write an address in here, and then we essentially jump out, right? So, and here is the outer end, and we actually jumped out, and everything is fine. Okay, I think that's what we have to do in here, right? If we put 4 in here, right, if we put 4, there will be like 1 iteration, and I think it was, all right, I'm pretty sure it was. Let me remove the this thing, and it was basically that. Okay, so this is a very small thing, right? So, but we want to go a bit bigger, right? So if I increase the amount of iteration, like 10, it seems to be working. What about 20? That works well. So I think that was the bug actually. So that was literally the bug. And I wonder. So how many iterations do I need to have in here? I may basically brute force that. I think, yeah, I think around 40 is a good amount of iterations. So yeah, so if I'm stuck, what I need to do is just like make a small break, make a cup of tea, and everything is gonna be okie dokie a karaoke. All right, so that's pretty cool. So we developed like a very simple Deque based language, not stack based, but rather Deque based language. And yeah, so we implemented rule 110 in it. So I think I'm gonna essentially yeah, I need to commit everything to the repo, right? So of course everything is going to be licensed under MIT, right? Then I'm also going to put a remin here. Deque programming language inspired by, and we're gonna give the link to here, right? Inspired by that. quick start console Deque pi rule 110 Deque. There we go. And let's confirm that it actually you know, works. It seems to be working. That's very, very nice. Git init. Right, and I'm going to do committee ready, set, go, and let me also create a repo. Deque pi. So what am I gonna put in the description? I don't even know what to put in the description. Like, I just like have to think. Deque based programming language, right? Oh boy, and let's just create that. Like, I feel like I need to put something more informative there, because like if people see it for the first time, it's going to be unclear what the hell is all of this about. But maybe that's just the nature of this project. I don't know. Maybe that's just the nature of this project. Okay, so I'm gonna push that right into the repo. Hopefully that was successfully pushed. And here it is. Here it actually is. So it's pretty cool. And it even turned it into a link. And let me put that in the description for everyone who's watching on YouTube. Where's my description file? MD, there we go. Source code is available in here. All right, so that was an interesting experiment, right? So Deque based programming language is in fact Turing complete. So, and we even have a proof. I'm not sure how good of a proof this is, but it's kind of a proof. And yeah, thanks everyone who's watching right now. I really appreciate it. Have a good one, and I see you on the next Zosin session, where we're gonna explore other interesting topics. All right. Thanks everyone for watching. Love you. Mwah.